All right, the squeeze theorem is listed here. Let's see if I can straighten this up a wee bit and tilt it in. That's a little better. The squeeze theorem, our 16th, I think, in our list. If h of x is less than or equal to f of x, which is less than or equal to g of x, so we have three functions going here. This one is always less than this one or equal to it, and this one is always less than or equal to this one. So for all x in an open interval containing c, except possibly at c itself for those badly behaving functions, and if the limit as x approaches c of h of x, remember h of x was this little guy, it equals the limit of g of x as x approaches c is L. So the little guy has a limit L and the big guy has a limit of L. So guess what happens to the function that's squeezed, sandwiched, pinched in between? It also equals L. So the limit of that function in the middle must also equal L. Let me show you to you with a picture. So let's say we have a graph, and first of all, h of x is some function like that, and we'll say g of x is some function. Oops, I gotta draw it so it has the same limit. That would help. Alright, we have to pick a spot C, so I'll pick C right here. So this will come down and hit that. So right at that point we have g of x. So the limit as h of x approaches c is the value L. We come from the left or the right at c, you'll see it has the same limit L on both sides at this point c. And so does g of x. So now let's say there's a function everywhere that is in between the two. So here comes good old f of x. So f of x is everywhere between h of x and g of x. So you can see then, if you can establish that there's a function that is always in between two functions that have the same limit at a certain point, then that in-between function must also have the same limit at that point. So that's what that means. So you can see the blue one, f of x, also has the same limit. So intuitively, that's not a very big jump to make. I think that should make perfect sense. So with that in mind, why are we doing the squeeze theorem? I mentioned that it was another way to find a limit, but the squeeze theorem is not directly used. This is used to prove something else that we will use to find limits. So let's go on to the next step for that. Over here, I'm going to take a picture of, let me restart my stop, clear, start. All right, so it took me about 5 minutes, I guess, to do that. All right, let's look at a limit. There's two special limits, and I have to prove them to be true. And I'll take the first one, because that's the one that, it turns out that this limit, the limit of sine x over x as x approaches 0, is going to equal something. And I'll figure out what it is as I prove what it is to you. So we'll go ahead and observe this. Suppose we have a circle, and that circle is a unit circle, and so I'm going to sit it on a coordinate plane. So everywhere the radius is 1, and I'm interested in an angle. So I'm going to pick an angle, and I'm going to establish a triangle on the unit circle like that. So it has the angle has degree theta, and this base right here, because it's on the unit circle is 1, and I can establish this point. The name of that point I can establish, and I'll need that, so I will establish that it is, because the first coordinate of any point on the unit circle is the cosine, and the second coordinate of any point on the unit circle is the sine, I'm going to call that point cosine sine, which is true no matter where we are on the unit circle. So that's that point right there. Now I need this point. This point is going to have the name of, well, let's think about it. Over here in our thought cloud, we have the idea that the tangent of that angle is the side opposite over the side adjacent. One of these we already know. Side opposite we do not know. Side adjacent is 1. So I can replace this as side adjacent with a 1, but that tells me now the tangent of that angle is the opposite. So the opposite side, I go over 1 to get to this point and up the opposite side. So that tells me this point is 1 over and tangent theta up. So I've established that. All right. There's some people rumbling around outside the room, so if they come in, I'll have to address that, so we'll see. All right. So now we've got that, and then this point right here, I'm going to do another color for that one, is 1 over and 0 up, 1, 0. So we're ready to go, ready to roll now. All right. Again, I'm trying to prove this special limit. This will come up all over the place, so I am going to prove it to you, and then as I prove it, you will know what to put in the blank there. All right, so this triangle, and I'm going to pick out, before I finish with it, I want to connect this point with this one. So now I have 2 triangles and a sector all in front of me. All right, follow along. Let's look at the big triangle. Let's look at the sector. And let's look at the little triangle. All right, the big triangle, I'm thinking about its area. So that's this yellow one. And the area of any triangle is 1/2 base times height. The base is 1. So I have 1/2 base 1 times the height is tangent theta. So I'll simplify that to tangent theta over 2. All right, is that showing up? It is. Now I'm going to look at the sector. I'll shade it in. It looks like the piece of pizza there. And actually, if you overheard what pre-calc was doing, I don't know if they've done it by this day or not, but I think they have. You'll hear it soon enough. We established that the area of a sector is 1/2 theta r squared. So I'm not going to prove that to you. It was proven last year. So here we have the area equals 1/2 theta, but r, the radius of our piece of pie, is 1. So this is just a 1, so we end up with theta over 2. And now we go to the smaller triangle, one with the orange side, and it's going to be 1/2 base times height. 1/2, the base, again, is 1. The height this time is this length right here. So what is that? Well, I went over cosine and up sine. So it's the sine of theta is the area. So area, so here we have sine theta over 2. Now what is the relationship of the size of these 3 pieces? This one is bigger than this one, and this one is bigger than this one. It shows up clear up here. So I now know that this tangent theta over 2 is greater than theta over 2, which is greater than sine theta over 2. So let me go ahead and, I don't think I need the squeeze theorem in all its glory. So let me make some room here. Come back where I started. All right, so repeating that, tangent theta over 2 is greater than or equal to theta over 2, which is greater than or equal to sine theta over 2. All right, our next little trick that I have in my mathematical bag is I am going to multiply these all by, since we have an inequality, as long as I multiply everything by the same thing, I will establish another inequality that is true. I'm going to multiply each side, or each portion by, let me come back here. Sorry about that. Come back here. So multiplying this through to all of these, you will see that we're getting somewhere. This times this, the 2's cancel, and I get tangent theta over sine theta. But tangent is sine over cosine, and sine is on the bottom. So all that leaves for me is a cosine. When I multiply this times that, the 2's cancel, and I get theta over sine theta. And I still have this inequality relationship. And then when I multiply this times this, I get a 1. So now I am going to use the reciprocal of all of these. And when I do that in an inequality, it will reverse the sign, the direction of the inequality sign. So I'm going to put 1 over cosine, the reciprocal. That causes this to reflip. Sine theta over theta. And the reciprocal of 1 is 1. So now I have a situation where I have made a mistake here. This sine over cosine, this is 1 over cosine. Sorry, up here. When I took tangent and changed it to sine over cosine, that should have been 1 over cosine. So when I flipped it, I get cosine. So let's look at the limit of this as, remember, the one we're trying to find out over here in the box is the limit as x approaches 0. I see that expression, sine of something, sine of an angle over the angle. I see that now has appeared right here, and I need a cameraman. Sine of theta over theta has appeared. So what is the limit of this expression as theta approaches 0? Well, we would substitute 0 in for cosine and get cosine of 0, which is 1, which is less than or equal to, this is the one I'm interested in. Is that showing up? Let me bend it down a little. And then this is the limit of this as theta approaches 0 is 1. So as I take the limit of each spot as theta approaches 0, I see a 1 on this side and a 1 on this side. So therefore, by the Squeeze Theorem, if this function is always in between these two and they go to 1, then this must also. So back to our box. The limit of sine x over x equals 1. All right. I think that's enough for now. There is another special limit. It's very quick to establish, but I don't know whether to do it or not. Tell me what to do. Let me give it to you, and I'll establish it next time. So another special limit. I might even be able to sneak it in class. So another special limit that we have to know by heart is 1, as limit as x approaches 0 of 1 minus cosine x over x, and that equals 0. I will prove that to you next time, either by video or in class. It's a much simpler proof, and I just feel like we've done enough. So if I ask you to do all 3 parts, I apologize, but not really, because that's where we